Welcome to the first breakout session post keynote. Thank you all for coming and probably racing over here from the keynote. I gather it ran a little bit late. It's going to be pretty full in here today, I understand, so I apologize for making you sit too close to your fellow VMworld attendees. If you really don't like being around other people, there are still some seats open at the back. My name's Bruce Davey. I'm the CTO for VMware Asia Pacific in Japan, so I'm quite a long way from home today. The reason I'm here giving this presentation is because up until about 2 years ago, I was the CTO for the networking and security team at VMware. And so the NSBU team asked me if I would be willing to continue to come and speak about what we're doing with NSX. And so one of the things that's been interesting for me in the last year or so is I've gone from being the networking person at VMware to being somebody who's expected to talk about everything that VMware does and to have opinions about what's going on all across the IT industry. So for example, about a year ago, I noticed that people kept on asking me questions about artificial intelligence, machine learning, blockchain, Internet of Things, and I sort of had to go and study and figure out what's going on in all those areas. So what I'm going to try to do today is not just talk to you about networking, but I'm going to talk to you about networking in the context of the broader industry, which is obviously a very exciting place to be right now. And I think most of you would have just come from the keynote where you would have heard Pat Gelsinger talking about the superpowers of tech. So I'm going to talk a bit about that in this presentation. Before I get started, this is a disclaimer. This is quite a forward-looking talk. I think most of what I'm going to talk about today is actually in the product, but just to be on the safe side, please don't assume that I'm promising any future capabilities in this talk. So as I said, if you were at the keynote, and I assume most of you were, you would have heard Pat talk about these 4 superpowers of tech. And the interesting thing for me was, just as I was noticing how everybody was talking to me about blockchain and IoT and AI, Pat started talking about these 4 superpowers, and I realized that these superpowers have a lot to do with networking. And I have actually a pretty broad background in computer science, and so I've worked in some of these areas before I got into the networking field, and I wanted to start by talking about a particular area where I had some history. The next slide may come as a bit of a shock, so just prepare yourself. In 1985, I actually started working in AI. And so I went to the University of Edinburgh. That's a picture of me from 1985. And there's probably lots of cautionary tales to be said about keeping track of your old student ID card. But anyway, that was me when I was a fresh-faced PhD student about to go and learn about AI. Now, the question that you might ask yourself is, why was I going to study AI in 1985? Well, it was obvious. In 1985, AI was just about to take off. And of course, it didn't quite work out that way. Fortunately, when I got to Edinburgh to study AI, I discovered there were actually 2 different departments at Edinburgh. There was a computer science department and an AI department, and I had actually registered in computer science. And the 2 departments didn't actually talk to each other. The computer science people thought that AI was really a collection of cowboys who didn't really have any kind of rigor to how they approached the problem. And the artificial intelligence people thought that computer scientists were all kind of stuck in the old way of doing things. So they didn't really talk to each other much. I went off and became a computer scientist. AI kind of went into hibernation. But then, 30 years later, AI is really taking off now. And I want to talk a little bit about why that is. And believe me, this will come back to be about networking. Just be a little bit patient. So here's an early piece of AI technology from 1963. This was a mechanical computer built by Donald Michie, who was the founder of the AI department at Edinburgh. And this mechanical computer consisted of a few hundred matchboxes, each of which contained a set of colored beads. And to play a game of noughts and crosses against this computer, a human operator had to go to the appropriate box that corresponded to a particular configuration of the game, open the box, pull out a random colored bead, and that would tell you what the computer's next move was. And so you would make a mark on the piece of paper and go through and play the game. And if the computer ended up winning, you would go back and put more beads into those boxes to reinforce the behavior that was winning. And if the computer lost, you could remove some of the beads to discourage the losing behavior. So this was reinforcement learning played by a machine in 1963. Now, as I said, AI did not really take off until about 30 years later, or actually 50 years later relative to this. Here's an example of what AI can do today. This is one of my favorite pictures of AI. You can tell there's a set of pictures of puppies and a set of pictures of muffins. And most of you probably think you can tell the difference. But in fact, a computer is better at this task than you. If I ask you to very quickly classify those as puppies or muffins, you will make mistakes on average at a higher frequency than today's best algorithms. So from 1963, where a computer could just about play a serviceable game of noughts and crosses, to today, where a computer is now better at doing machine learning for image recognition than humans, we've come a long way. What has changed in those last 50 years? Well, a really big thing that's changed is the amount of data that we can feed into these algorithms. And another big thing, of course, is that we've got massive amounts of compute power to throw at these problems. So whereas 50 years ago, if you wanted to study AI, you could build your own computer out of matchboxes. Today, if you want to study AI, you can go and rent some GPUs running in a cloud and then take all of the magnificent data sets that are made available, thanks to many of you uploading and tagging your photos of cats, so that we can throw huge amounts of data at this problem. And AI today fundamentally thrives because of the data, and that's the thing I'll come back to that really strongly relates to networking. The other topic I've had a bit of history with is IoT. This is an environment pretty similar to where I worked as a summer student in 1983, working for Australia's largest mining company, BHP. And my job in this experiment was to sit inside an iron ore truck while we drove around an iron ore mine, picking up 200 tons of iron ore at a time. The reason I was doing this was because the trucks were breaking much more quickly than we expected. And so my co-workers had come up with a system where we put analog strain gauges all over the truck in about 20 different places. We ran wires back from those strain gauges to a data recorder that sat underneath the cab of the truck. And then I sat inside the cab of the truck and took notes. So I would write 10:15 received 200 tons of iron ore, 10:20 went over a bump, 10:25 dropped off the iron ore. And over the course of 2 weeks, we accumulated a decent amount of data. We took all the tapes, we sent them back to Melbourne, we digitized them, and we studied the data and figured out where were the weak spots in the truck. Now, this was 1983. If you were going to do this today, you wouldn't take a 20-year-old student and put him in an iron ore mine. You would actually go and put a bunch of IoT devices on the truck. It would be little tiny compute nodes with cheap wireless capability, sending all the data back to some local compute, some edge computing node that would then send it off to the cloud for analysis. So the difference between IoT in 1983 and IoT today is just because of advances in computing and networking, we can almost for free instrument all of these kinds of systems and gather massive amounts of data. And again, we get this huge amount of data. We can now start to feed that into our machine learning algorithms. So as I think Pat mentioned, the superpowers actually feed each other. As we get better data from IoT, we get better results with our machine learning algorithms, for example. As we get better clouds, we have better capability to analyze that data. And today, IoT is big business. Hundreds of millions of connected devices, connected vehicles, trillions of dollars spent. Interestingly, lots of lost medical devices, and I'll come back to that in a second. Terabytes to petabytes of data coming out of various systems. It's just incredibly easy now to start instrumenting devices and getting data and analyzing that data and using it to improve the way we run our businesses. And the problems that now come up when you think about that environment are, how do you manage those billions of devices? How do you manage those petabytes of data? And how do you keep all that data secure? If we're thinking about medical data, for example, you definitely don't want your medical data getting lost. And yet these are often very small, very cheap devices that don't have very strong security built in. So those are just a couple of stories about some of the tech superpowers. What does this have to do with networking? Well, you'll notice I said several times, this is all about getting access to massive amounts of data, feeding it into algorithms, putting it into the cloud. Data is what really drives most of IT today, and indeed drives a lot of business. But data has changed. Once upon a time, our data lived in a data center, and that was all we had to worry about. And so as you may know, I've been doing networking for a long time. As you maybe gathered from some of my stories, I've been around a while. I actually started working on networks in 1988. We built data center networks in an era when data lived in the data center. But today that's no longer true. Today, data lives out at the edge in these IoT applications. Data lives in the cloud, where we're putting it for analytics or for access to cheap computing power. Our data is more distributed than it's ever been before, and it's also more voluminous than it's ever been before. And it's so central to our businesses that securing that data has never been more important. So where this leads me is to say we need to be thinking differently about how we do networking, because networking is not the same as it was even 5 years ago. You cannot simply go and build a really good data center network and declare success. That's the way we did networking for most of the last 30 years. We built networking appliances, be they firewalls or switches or routers. They were physical objects. We put them in a data center, we programmed them or we configured them, and they did their job, and we could consider that to be a pretty good network. Today, that's not the way the world works. Our data is fully distributed. Your application that is today running in your data center, tomorrow could be running in the cloud. Another day, it could be out running at the edge. If you need some networking capability or some security capability, it needs to go where the data is. And that means it can no longer be tied to a physical object sitting in a particular location. What we need is flexible, programmable network capabilities that go where the data goes and go where the applications go. And those data and applications are more distributed than they've ever been. So this led us to this idea of the virtual cloud network. And this was a term that was coined by VMware back in about May of this year, and you've probably heard it by now. It's really not just a VMware thing. This idea of the virtual cloud network is actually the way the entire industry is going. You can find articles by analysts talking about this. You'll find documents coming from our competition talking about how they're embracing this kind of view. They may or may not call it the virtual cloud network, but you have to have a network that is fully distributed and where your applications and data can be fully distributed, and the networking and security services can be deployed wherever the applications and the data go to. So the interesting thing about this is, as I said, we first started talking about the virtual cloud network in May of this year, but we've actually had this kind of model of networking going wherever the data and the applications go for a long time. This is actually a pretty old slide that I think I used at VMworld 3 years ago, and it was at the time our vision of what we're doing with NSX. The idea that NSX was not just about securing applications running in virtual machines, running inside your data center, but that it was also about connecting and securing your applications in the cloud, connecting and securing your data out at the edge, doing this for containerized workloads as well, doing it for the branch. So we've had this vision for a long time. The thing that's really cool is that today we've actually implemented everything in that vision. And so this is the modern version of that slide, which basically describes what NSX does today, including connectivity to the branch, security for end users, networking services for clouds, containers, and so on. So what I want to do in the remainder of the session is I want to go a little bit deeper onto what NSX actually looks like today, how we've implemented it, and how it does all these great things that I've just described, how it can give you this kind of connectivity and security wherever your application is, no matter what form factor it runs in, no matter where it's located. And I want to go back and talk a little bit about history again, because you can tell I like that stuff. Anybody recognize either the people in this picture or the computer? Okay, what's the computer? PDP-11 and Dennis Ritchie. That was very good. And I think the other person who's not Dennis Ritchie is Ken Thompson. Fantastic. Okay, prize for you. So why have I got this picture here? Well, it turns out the first internet routers were actually built on PDP-11 style computers, but also there are two fundamental problems that we've worked on in networking for as long as I've been in the field and even longer, which are heterogeneity and scale. That one of my close colleagues in my early career was the person who invented EGP. Anybody know what EGP is? A few old timers. It was the predecessor of BGP. You've got to be really old to know about EGP. But so this friend of mine said, the only hard problems in networking are problems of scale. And it's roughly true, because if it weren't for the scale, you could kind of hack some solution together for most of our networking problems. But once you try to think about how do you do things at scale, a lot of things get harder. And this has been as true for network virtualization as it is for traditional networking. And so for as long as I've been involved in NSX, which really goes back to my days at Nicira in 2012, we've been tackling these dual problems of heterogeneity and scale. Heterogeneity being the problem of how do you get connectivity to all these different kinds of endpoints, whether they're IoT devices or containers or virtual machines. And so I guess I should probably pause at this point and say, how many people are pretty familiar with NSX, have been to at least one NSX breakout before today? All right, so that's probably half the room. So I apologize to the rest of you, because this is kind of an advanced session, but I'll just maybe spend a minute trying to level the playing field for those who are still learning their way about NSX. So NSX does really a very simple thing. It lets you specify your networking policies through a central point of control and then implement those policies in a distributed way out at the places where the applications and the data are. So it does that through having a central management plane, which is where humans interact with the system and also where APIs will come in from other systems. It has a central control plane, which does all the calculation to map between the thing that's been requested by the user and an implementation of that request. And then out at the edges, it has the data plane, which is where all of the actual application code runs and where we actually implement networking policies. Now, historically, if you were looking at NSX-V, the only kind of endpoint that we had was a virtual machine. And so the data plane was always the virtual switch inside vSphere. But today with NSX-T, we have many different kinds of endpoint. We have endpoints that are still vSphere virtual machines. We have KVM virtual machines. We have containers. We have bare metal Linux hosts. We have things running in public clouds. So we have a very diverse set of endpoints. That's the heterogeneity piece. We also still have the problem of scale, which is how many containers does it take to run a modern application? How long is a piece of string? It can take thousands of containers to run an application, so there could be thousands of endpoints that you need to provide networking and security services to. So going back quite a few years, we figured out that the first thing we needed to scale was the control plane. So while the control plane looks like a logically centralized thing, it's actually implemented as a cluster of tightly coordinated machines. So whether you're talking about NSX-V or NSX-T, it's actually a cluster of 3 nodes at a minimum that communicate with each other and arrive at a consensus about what's the right thing to do. And so they take their inputs from the management plane, do some calculation, and push out programming rules to the data plane to say this is how you implement a particular networking policy. And we've used fairly standard clustering techniques from the beginning. Things like Paxos and Zookeeper, if you're into that sort of clustering technology, have been used to provide the core underpinnings of building a scalable, logically centralized control plane. But we figured something out as we started moving into this world that's more heterogeneous, which is that we could actually make a new partition of responsibility between the control plane and the data plane that would be both more scalable and more accommodating of this new heterogeneous world. And so we decided with NSX-T to split the control plane into 2 parts. There's a part called the central control plane that does the things that are still centralized, and then there's a thing called the local control plane, which adapts the central decisions and maps them onto locally meaningful actions. So for example, if I want to program a firewall rule into a container, that's a slightly different thing than programming a firewall rule into a virtual machine. But the basic idea is the same. So I figure out, sitting up in the central control plane, what firewall rules do I actually need to implement? And then I send those commands down to the edges saying, please implement a firewall rule that lets this device communicate to these devices on these ports. And then the local control plane takes that set of instructions and translates them into something that actually is meaningful for the local environment. So we've taken a lot of the complexity of managing heterogeneity and we've hidden it from the central control plane. We've pushed it out to the edges where we can scale it much better. So there's a little local control plane running in every end host, whether it's a vSphere host, a KVM host, a cloud node, or a container host. Okay, so heterogeneity and scale, classical problems of networking. But there's a new problem that we have to deal with in the modern networking environment, which is agility. And interestingly, this is kind of something that we knew back in at least 2012 when we were working at Nicira, that we needed to have a way of provisioning networks that was more agile than the current state of the art. I'm sure most of you at some point have tried to configure a switch or a router using the CLI, and if you're sufficiently skilled, you can do that in a matter of minutes to hours, depending on the complexity. But the entire process of provisioning switches and routers at scale and doing it in a way that maintains correct security and doesn't cause outages often leads to weeks or even multiple weeks of delay between wanting a change and getting that change implemented. So networking for many, many years has been the thing holding back agility in the modern data center. Now today, of course, that kind of lack of agility is becoming increasingly unacceptable in a modern data center. And there's a number of trends that are driving this requirement for agility. So for example, you may have heard the term infrastructure as code. I think it was popularized by companies like Facebook, but the idea is pretty widespread now that you should be able to manage your infrastructure the same way you manage application software, which is to say, it's bundles of bits, you put it in version control, you can push out new versions, you can have automated testing, you treat it exactly the same way you would any other piece of code. Once you start thinking of infrastructure as code, you need to be thinking about your infrastructure as being completely programmable. You can't have a human in the loop if you're going to be doing things like automated testing, automatic release management, automatic rollback, and so on. We've probably all heard the DevOps movement talked about at great length at this point. More and more, the rise of DevOps means that if you're in IT, you're expected to be able to deliver services at the speed of developers and do it using tools that are familiar to developers like scripting, and to be able to do it in a way that's programmatic. And indeed, the number one thing that I think of when I think of DevOps is the breaking down of a barrier between the application owner and the IT owner so that they collaborate together to actually deliver a service that meets the needs of the business. And then finally, we've all had this experience at this point of everything being delivered as a service, whether it's through things we do as consumers or things we do in our jobs. But the idea that today you can go to Amazon or Azure and have a large amount of infrastructure provisioned for you in a matter of seconds has become pretty much the expectation of modern business and of modern users. And if IT can't deliver that experience, then they're quickly viewed as being irrelevant to the business. And so it's just become a mandate for IT that we can deliver that as a service experience, because that's what businesses and users have come to expect. So all of this means that our systems have to be capable of being driven by code. They have to be capable of being programmable so that you don't have to have a manual human process every time you want to make a change to something in the network. The fundamental interface to NSX is no longer going to be the UI, although the UI will always exist. It will be the API, because there will be other pieces of code that will be provisioning networking components. Now, if you think about, say, a modern environment running Kubernetes, and we'll show you one of those in a few minutes in a demo, there are going to be potentially thousands of API requests per second coming in to the networking system saying, you need to change this switching port, you need to change this firewall rule. These requests will come in fast and furious, so a network virtualization system like NSX has to be able to receive those very rapid requests from APIs. Now, what this means is you have to build a system that can receive API requests, acknowledge those API requests, and store the intent of those API requests very quickly. The actual implementation of the requested service could take a little bit longer, but at the very minimum, you have to receive requests, store the intent, and reply back very quickly. This led to us realizing that we needed a new persistent storage layer inside the management plane of NSX, and that's what I'm going to describe in the next couple of minutes. There's a piece of technology here called Corfu, and I'll give you a very quick overview of how Corfu works. If you want to learn more about it, you can actually go look it up on GitHub. It's an open source project that we started at VMware, and you can actually get the code and play with it yourself, but there's also some really good papers there describing the technology behind it. So here's the basic idea. Corfu implements what's called a distributed log. And first of all, I want you to think a little bit differently about what a log is. A log is not just something where you get all the errors in a system. An error log is an example of a log file, but it's just an example. A log is a data structure that you only ever append to the end of it. It happens to be a very efficient way of storing a list of transactions. So it's actually a pretty good way to implement an API service, because every time an API request comes in, you can append it to the end of the log and then come back and say, yes, I've got your request, I will get to it, trust me. Now that log has to be implemented efficiently, and it has to be done in a way that you never lose anything that you've written to the log. So this log is actually going to sit underneath the management layer. We'll put our API request into it, and then the control plane can consume information out of the log as we write stuff into it. There's a couple of tricks here, and I'll just warn you now, the next two slides are kind of pretty, I'd say, geeky, computer sciencey slides. I think this stuff is really cool. You may not agree with me, so it's fine if you want to check email for another next 2 minutes. But the basic idea is API requests are coming in really fast. You want to store as many of them as possible. So the first thing you would say is I should parallelize it. So when one API request comes in, I'll write it to a particular piece of storage, but when another API request comes in at the same time, I want it to be at the end of the log, but I don't want to be writing to the same physical storage media. I think I told you what logs are. So the idea is that as we do this, there could be multiple different physical disks on which we're storing this log. Let's say log entry 13 could get written to this disk, and log entry 14 could go to this other disk, so we can do the writes in parallel, thereby speeding it up. But we can also split the writes out and do them multiple times. So in this example, I wrote the log entry 13 to 2 places and log entry 14 to 2 other places. So I've got high scalability and high availability by implementing this distributed shared log. Now the hard part about this is, now that I've taken my transactions and spread them out across all these different disks, how do I make it look to the programmer and to the overall system like it's one simple data structure that just has a list of transactions in it? And that's where I get to the most fancy PowerPoint of this entire presentation. An API request comes in, it's going to get handled by one compute node. That node goes to a logically centralized sequencer and says, where should I write the next entry in the log? The sequencer says, you should write that to location 12, and there's a layout manager that says, and by the way, location 12 corresponds to these 2 physical disks. So at that point, the API request can be written to a couple of disks. You'll notice that the writing is nicely parallelized, and the only things that were centralized were the generation of a sequence number and the providing of this layout map, which is reasonably static. At the exact same time, another request comes in that says, I need to write to the log. He gets a different sequence number because that's the job of the sequencer, to never hand out the same sequence number twice. So he hands a different number, in this case 13. He hands the layout, and those transactions get written to another place. Okay, so just to wake everybody up, let's talk about blockchain. Why am I talking about blockchain, you ask? Because blockchain is actually a system for storing a distributed ledger of transactions, which is what I was just talking about when I talked about Corfu. I'm mostly talking about this just because I think it's kind of cool, but it turns out the underlying technology to build a distributed shared log for NSX and the underlying technology to build a scalable blockchain service have some things in common. They're not by any means identical, but they leverage some of the same computer science techniques. And coincidentally, I assume you all noticed in the keynote this morning that we announced a blockchain service that VMware is now making available, at least in beta form. VMware's been working on blockchain for about 4 years. And the people who work on blockchain at VMware are actually the same people who work on Corfu, because it is, broadly speaking, the same problem. How do you build a distributed log of transactions? By the way, how many people here have invested in cryptocurrencies? And how many of you have made money? Okay, congratulations to those 3 people. So when all the hands in the room go up, I know it's time to get out of cryptocurrencies. But so the blockchain technology, I hope you realize, is fundamentally useful for a lot of other things other than cryptocurrencies. But the reason I mention it here is just to say there's some similar computer science ideas going on there to what's going on inside NSX. The interesting thing about what we're doing at VMware is we don't rely on proof of work, unlike the cryptocurrency kind of approaches to blockchains. Instead, we're relying on a thing called Byzantine fault tolerance. And again, you can go look that up in your spare time. But the thing that I think is most cool about what VMware is doing on blockchain is similar to what's cool about Corfu, which is that we've produced a system that's incredibly robust and scalable. So does anybody know how quickly Bitcoin processes transactions in terms of transactions per second? Anybody want to take a guess? Yeah, the 5 is about right. It's in the range of 5 to 10 transactions per second. So the throughput here that we're getting with our blockchain implementation is on the order of 5,000 transactions per second. So just to put it in context, the blue line was the previous state-of-the-art before we started working on it at VMware. Similarly with latency, the typical latency for a Bitcoin transaction is about 1 hour. That's how long it takes before you can really be confident that a transaction is committed in Bitcoin. We're getting latencies in the 20 to 30 millisecond range. So just to give you a sense of like how far blockchain implementation is ahead of cryptocurrencies. Okay, so back to networking, and why does this all matter? So what I've tried to show you so far is some of the design decisions that we made. How do we make a networking system that responds to some of the needs of today? What I'm going to show you in the rest of the presentation is how that actually can impact your real life as you use this to solve some of your problems in supporting modern applications. And I'm going to focus in on Kubernetes. It's not by any means the only environment of interest to us, but I think it's one of the ones that has the most sort of buzz around it at the moment. And again, you should have heard plenty of talk about Kubernetes in the keynote this morning. And I'm going to guess probably most of you haven't spent that much time playing with Kubernetes. How many people have installed Kubernetes in their lab or on their laptop? Yeah, probably a couple of dozen people. I did it about a year ago on my laptop. It's actually quite a fun experiment if you want to do it. You can easily figure out how to do this at home. It's probably 15 to 20 minutes worth of work to get a minimal Kubernetes installation on your laptop that you can play with. For those of you who haven't played around with it, Kubernetes is actually not that complicated to understand. It's incredibly rich in its feature set, but it does a pretty simple set of things. If you think about a modern application, it's going to be made up of a lot of containers. And those containers need to run somewhere, and you want to make sure that the right number of containers run and that they deal with things like the scaling out as you get more demand for the application, failing over when pieces of infrastructure fail, all the things that you would typically do in a modern environment with virtual machines, but you have to do it with containers too. And one of the reasons why Kubernetes has been so popular is because it's a really powerful way that makes it easy for developers to build these services and applications that are made up of many, many small containerized components. So Kubernetes has these apps running in containers. Those containers run on nodes. A node could be a virtual machine or it could be a physical machine. If you look inside a node, you'll actually see these things called pods, and pods are just really groupings of containers that have things like an IP address and some other things in common, maybe a bit of storage. And inside a single Kubernetes node, there's a couple of processes like a Docker runtime to let you execute containers, and a thing called the kubelet that lets Kubernetes control plane interact with everything that Kubernetes is doing. That's the fastest tutorial you'll ever get on Kubernetes. Now, in a few minutes, you'll see a demo where we actually use Kubernetes to run a real application. I just want to talk a little bit about the relationship between NSX and containers. Containers don't have the same strong isolation that virtual machines have. They have isolation at the operating system level, but they're not as strongly isolated as virtual machines. So if you're running containerized apps, you need to be thinking about how do I provide networking and security services to those containers. And just to give you an example, here's what happens if one of your containers gets hacked. The malware comes in, it gets into the container. It can, if it's a good exploit, make its way through the container host into a completely different application, and then use that application to get to another machine to get to your critical data. It's obviously a simplified example, but it's kind of important that you think about providing security services to containers. So, this is where NSX comes in. And my demo helper is going to start getting us set up here while I talk a little bit more. So, NSX, and I'm specifically talking about NSX-T, has been engineered to help you provide networking and security services to containers, and also to cloud applications. We're going to focus on containers right now. Now, you'll see in a minute just how easy it is to create a container with Kubernetes. It takes a matter of a fraction of a second. So if containers are getting created by Kubernetes at such a rapid rate, you have to be able to automatically spin up the appropriate networking services and automatically connect them to the containers to provide whatever the intended policy is. So you can specify your policy ahead of time, but once Kubernetes takes over and starts spinning up containers, you need the entire networking piece to be automated. So what NSX does is we have a plugin that sits between Kubernetes and the NSX manager, and it looks for things that are going on in Kubernetes, like the creation of a new container. And when it sees those things happen, it makes an API request into NSX to say, here's the appropriate networking policy to apply to that container. So in a minute, we'll show you this demo. And the demo is going to be, it's a real live demo. This is legit. It's actually running in our data center. Where's the data center?
In Vegas.
In Las Vegas. So we're relying on good network connectivity as well. The way this application works is we've got a MySQL database that has all of the static information about the current set of planes registered with the Federal Aviation Administration in the United States. Sitting above that, we have an application tier which is able to run queries against that database. We've got a front end that lets us interact with it through a web page. Both that front end and that application tier are running as containers, whereas the MySQL database is running as a virtual machine. So you're going to see a bit of heterogeneity in this demo. There's also a thing called ADSB, which is this amazing service that you can get off the internet that tells you where are all the planes in flight right now. So we're going to build another application that pulls data from ADSB and then sticks it into a Redis database, a NoSQL database, and then we will correlate the information in Redis with the information in the static database to show you where a particular plane is in real time. That's the plan. Okay, how are we doing?
We're ready.
Okay, so let's switch over. Okay, first of all, something to make you feel comfortable. Here is the vSphere client, and you can see a few nodes there. There's a Kubernetes master, which is where the control plane is, the Kubernetes worker, where we run the containers, and the MySQL virtual machine, where the static database is. We've done a little bit of pre-work here to make this go faster. We'll go start over in Kubernetes. Everything we do with Kubernetes in this example comes from the CLI. So we've partially deployed some of the app. We've got a namespace called Planespotter. And I think if we look inside that, we should see we've got a few pods running. And those pods, there are 4 of them, and they correspond to 2 components of the application, the part that talks to the MySQL database and the part that serves up the front end. And so when we go and look at NSX, you can see that we created a logical switch automatically to correspond to the Planespotter namespace. And we've also got a logical port on that switch for every pod. So there are 4 pods, and there are five ports on the logical switch. You'll see this will change as we deploy more stuff with Kubernetes. So getting back to Kubernetes, we can look at what's called the ingress for the service. And the ingress is actually a layer 7 load balancer that's sitting at the front end that lets us interact with the application. It's actually provided by NSX, and it tells us that planespotter.corp.local is where the application is. So let's go over to a browser and look at the application. Okay, good. There's our application. That's the front page. It has built-in application health monitoring. If we go look on that, you can see several things are running correctly, but we don't have connectivity to the Redis server because we haven't deployed it yet. That's the bit we're going to do next. And now if we just go look at the actual user interface, we can look at the list of all the planes in the FAA database. We're going to search for all planes from American Airlines, just as an example, and you'll see lots of planes there. Tells you what kind of, lots of Airbus planes, nice European planes. And then we don't have any of the airborne data yet. We'll get that in a minute. So let's go back to Kubernetes and deploy the rest of the application. So we're using this command called kubekettle. It's got a specification of what the application is supposed to look like, and it's deploying a few more pods, one to talk to ADSB and one to deploy the Redis database. And so now if we go look at NSX, hit refresh. Okay, we got more logical ports were automatically created on that switch. So all of those containers that we deployed have now been connected to a single NSX switch, so they're all communicating with each other. Very simple networking functionality. Let's see how the app's working. Okay, everything's green, so we've got Redis connectivity up. Let's go look at the planes again. We'll search once again for American Airlines. Okay, so anything green should be airborne. Let's click on one. And there we go. We've got a picture of a plane in the air, and it's flying from Philadelphia to San Diego. So this is legit real-time data. That plane is really in the air right now. Okay, let's see. I think we want to go back to look at Kubernetes again. We're just going to show you that we actually did deploy those pods. There you see the extra pods for the Redis piece, and now we're going to look at YAML. So this is the actual specification of the application. A lot of stuff here, but this is how Kubernetes knew what it was doing. It deployed pods based on information in this YAML file. But NSX also understands things in this YAML file. For example, there are tags that are meaningful to NSX, like the name of the application and the tier of the application can all be included in tags, and we can use those tags to build firewall rules. Let's go look at a firewall rule. So we've got one that lets the application tier talk to the MySQL database. It's leveraging those tags that we saw a second ago, and we're going to go in and mess around with this firewall rule. So currently it allows communication from the application tier to the database. We're going to break that communication. Okay, we save everything. So now if we go, I guess, look at the application and see if that did anything. Yes. So if we go to application health, okay, immediately database connectivity failure. Let's look at the front page of the application again, just to see what it did to the actual application. Oh, yep, it definitely broke the application. Okay, so let's go back to NSX now. Now we can actually troubleshoot this problem with NSX. Of course, we created it, so we kind of know what's going on here, but here is a trace flow that's letting us trace from the application tier to the MySQL database. We ran this trace earlier when everything was working, and it showed us every single thing that happened as a packet went from the application tier to the database tier. It was all the way through the NSX data path, every single thing that was done to that packet. Now, if we just go and retrace, it'll help us find the problem. This will take a few seconds. Again, live demo. What version of NSX is this?
2.3.
It's version 2.3. There we go. We very quickly saw the trace flow came back with the answer that this firewall rule is dropping the packet, which is, of course, exactly what you expected because we deliberately broke the firewall rule. But what this kind of shows you, I think that's it for the demo. Thank you so much, Marcos. All right. So that was Marcos Hernandez, one of our star field principal engineers and demo master extraordinaire. So that was absolutely legit. We didn't fake anything in that demo. So what you just saw was how we built the application, and we could troubleshoot networking problems as we were automatically deploying networking services in response to the application being deployed using Kubernetes. So to me, this is a really happy situation for networking to be in 2018. Oh, we did that. So we have this new world where everybody wants their applications deployed really quickly. And so, you know, you have an idea, you give it to a development team, they just want to run. But meanwhile, we expect IT to maintain security, availability, performance, to troubleshoot. And so what you saw in this demo was all of the policies for networking were set a priori. So for example, we had a policy about letting the application tier talk to the database tier, but we could have set that up weeks ago. The Kubernetes tags automatically caused the right policies to be implemented in real time as Kubernetes was deploying and life-cycling the application. If you then went and uninstalled the application with Kubernetes, NSX would also go and uninstall the networking services automatically. So IT gets to deliver the exact service that the business needs. It's secure, it's compliant, but it's also timely. It's not in the critical path. It's not preventing the business from moving at the speed of the application developer. So to me, this is really the future of networking, when you can say networking moves as fast as the public cloud, but it lets IT and the business continue to do the things we expect around maintaining security, compliance, adherence to policy, controlling cost, and all of those things. All right. So in the last 10 or so minutes, I just want to switch gears real quickly and talk about the WAN, because I've talked about NSX for a lot of different things, but there's this whole other direction of the future of networking, which is changing the WAN. So let me give you another bit of history. By the way, for all the young people in the audience, this is your future. When you get old, you will talk about your past. That's the way it goes. So in 1997, actually a little bit prior to that, I had the good fortune to be working with a team of people who were creating MPLS as we eventually came to know it. I did a really clever thing. I co-authored a book with Yakov Rektor. Yakov Rektor is one of the most brilliant networking people in the history of networking. He's on the RFC for BGP. He's on most of the RFCs for MPLS. So sometimes people refer to me as the father of MPLS. That is flat out wrong. Yakov is the father of MPLS. I am the co-author of the father of MPLS, which was a pretty good career move. So MPLS was a really good way to build VPNs in 1997. It was the best thing we could think of at the time, and one thing we knew in 1997 was centralized control did not work. Now, think about everything I've told you in the last 45 minutes. Most of what I've talked about is how NSX scalably implements centralized control. So what changed between 97 and 2018? Basically, a whole lot of computer science went into building scalable, highly available centralized controllers. A lot of the work that went on at places like Google was based on building these clustered systems. Things like Corfu, things like Zookeeper, all happened in the gap between sort of 97 and 2018, so that we learned how to do centralized control. That's why NSX works today. Now, in 2013, one of my co-workers from the Nicira team decided he was going to go and try something else. He went to a startup company, and he told me what they were going to do. He said, we're going to build a software-defined wide area network that builds tunnels between all of the branches using a logically centralized controller. So basically the same thing that we had done for the data center, his company was going to go and do it for the WAN. We didn't actually have the term SD-Wan at that point, but that was the first time I heard anybody talk about SD-Wan, and I immediately knew that was a good idea, because it was a new piece of information that we didn't have in 1997, which if we had it, if we knew how to build centralized controllers in 1997, we would have done things differently. with that new knowledge of how to build centralized control, SD-Wan became possible. In 2018, of course, actually 2017, VMware acquired VeloCloud, thus entering the SD-Wan market ourselves. And tomorrow I'll be doing a much longer breakout session on SD-Wan. So just real quick, and you should definitely go see a full session on SD-Wan, but just to give you the real highlights, what does SD-Wan fix about networking? Well, if you've ever tried to order an MPLS circuit from your favorite service provider, or if in fact you work for a service provider, you know that it takes a while to deploy MPLS circuits. And if you're building a VPN with MPLS, you just don't have that many options. You end up spending whatever the service provider wants to charge you. You maybe have a choice of a couple of service providers. And you also often end up with taking traffic from the branch all the way into your central data center, only to send it out to the cloud because more and more of your services live in the cloud. So what changed with the arrival of SD-Wan was we could now build a much simpler system where you can drop a virtual machine or a physical appliance at the branch. It automatically connects to the central controller. It figures out where it needs to build tunnels. It builds them all automatically. And now you can have deployment in a matter of days. Direct access to the cloud with built-in security, even though you've got direct access from the branch. You can now use any number of different transports because you can build these tunnels on top of any form of physical connectivity, whether it's MPLS or commodity broadband or LTE, whatever your favorite choice of link is. And then finally, you can now start to do intelligent quality of service across these parallel links. And the idea of assured application performance is actually one of the things that's really distinctive about VeloCloud in the broader SD-Wan market, is the VeloCloud team really figured out how to take 2 or 3 or 4 parallel links and make them behave like one really good quality link, even if the individual links themselves were not such great quality. The other thing that's interesting is once you combine the power of SD-Wan with the power of NSX, you can now start to have coherent security policies that go all the way from the data center to the cloud to the branch, which gets back to that vision of NSX that I was talking about earlier. The idea not only that you can have modern, agile, software-defined connectivity wherever your applications run, but that from a single central point of control, you can say, this is my security policy, this is my networking policy, please implement it all the way from the branch to the data center to the cloud. And so as we more tightly integrate the VeloCloud technology with NSX for data center and NSX for cloud, you'll see more and more integration of how you specify your security policies consistently from end to end. And this is a quick example just showing, here's one policy for customers coming in on the internet, another policy for your very sensitive payments microsegment, and yet another policy for bulk data, each of these being put into different microsegments that extend all the way out to the branch. So that kind of brings me to my conclusion. So I've talked a lot today about how networking is changing, and hopefully I've given you both the big picture of why networking needs to change and where we're going with the future of networking, but also given you some concrete things that you can start to work on today. I'm mostly focused on NSX-T and what it can do for things like Kubernetes, but across the NSX portfolio, we've got you covered whether it's your cloud workloads, your traditional vSphere workloads, your bare metal Linux, your branches, your IoT devices, all of those things, we can provide consistency of networking and security across all those kinds of environments. So I want to leave you with a couple of thoughts. As people who bothered to show up to the first networking session offered at VMworld Europe 2018, you have the potential to change the way networking is done. I'm sure many of you are people very focused on the networking part of your business. Some of you are probably networking experts. I hope to have given you a bit of a sense of how dramatically networking is changing from the way it was done over the last 30 years to the way it will be done for the next 30. And you have the ability to really take part in this transformation. NSX is the tool that will help you do that. You can start small, you can find a single use case in your company and go tackle that, but ultimately you can transform the way networking is done to make the IT department and the networking department more valuable to the organization you work for. And you can really be the people who drive change throughout your organization. So, as I think I've said every year for the last 6 years, it's an incredibly exciting time to be in networking. I've been fortunate to be part of this transformation of networking as NSX has matured and gone into new applications and new environments. I hope each of you will take the chance to get more knowledgeable and more hands-on with NSX during your time here. There's a few things you can do this week. I can see that I didn't do a good job of updating my slide here because it's got a couple of references to things that happened in August at Las Vegas, but you should really go do the training, go do the hands-on labs, and go look at your schedule to figure out which sessions are going to be happening over the rest of the week. I've got 4 more sessions that I'm speaking at this week. If you really enjoyed my talk, you can get to hear me again. If you really didn't enjoy my talk, there's lots of other options. By the way, if you enjoyed my talk, there is a survey that you can fill out, and we really appreciate it if you would fill out that survey and let us know how we can keep on making VMworld a better experience for you. With that, I will just say thank you very much for your time. I'm happy to take the last couple of minutes for Q&A.